Exato, essa aí mesmo. O de baixo. Now, the next session of our workshop. So during the afternoon now, we have several presentations, right? We are going to start then the first one with Professor Josef Nossek. Professor Josef Nossek received the Diploma Engineer title and the Doctor PhD degree title in Electrical Engineering from Vienna University of Technology, Austria, in 1974 and 1980, respectively. From 1989 to 2016, he has been the head of the Institute of Circuit Theory and Signal Processing at the Technische Universität München in Germany. In 2016, he joined the Federal University of Ceará as a full professor. Okay, so now I'm going to pass the word to Professor Nossek. Thank you very much again for being with us. Okay, great pleasure, please.
Yeah, good afternoon to everybody. First, I would like to thank João Paulo for inviting me to talk here to you. What I will tell you is something about physically consistent modeling. And the theoretical framework I'm using, I'm sure almost every electrical engineer knows, has learned in the undergraduate program. But when they later go into, for instance, information theory, communication theory, they seemingly forget that. And that is what I would like to bring across. By the way, this is a short version, an introductory short version of a tutorial, which I will give in 3 weeks from now at the CAMSUP conference. So there at the conference, it will be a 3 hours tutorial, and what you get is a very short version of that. So as I said, it's all about modeling of physical systems, and any model, as we know, is always an abstraction of reality. It's a simplification of the rather complex reality. And there may be a number of different models for the same system, depending on the phenomena we are interested in, which we are looking at. Anyway, whatever model we choose, then we do analysis with that model, we may optimize parameters of the model, and finally we have to check with reality, with measurements, whether we really have captured the important effects and whether there is an agreement between our analysis and the measurement will tell us whether we have to change the model or simply can be happy about the model which we have already used. For that, I will show you a very simple example. That is, imagine you have 2 lambda over 2 dipoles perpendicular to that screen, and from the far left, there is a plane wave coming where you see the wavelengths of that harmonic wavelengths also seen there, and we try to measure the phase difference of the 2 signals which are picked up by the 2 antennas. And the expectation, and what's in the most signal processing literature given, is that these phase difference grows linearly with the difference between the antenna elements. And when the spacing between antenna elements is lambda over 2, then we would expect a 100-degree of phase difference between the 2 signals. And that signal and that phase difference will go towards 0 if the distance goes towards 0. Is that true? No, this is wrong. And the reason why it's wrong is that it assumes that the antennas can sense the field without changing the field. And that's, of course, not possible. As soon as the incoming field is inducing a current on the antenna structure, there is a scattered field, and that superimposes the incident field, and therefore things change. And the right answer is this one, which is quite different from the first one. To be honest, it's also not completely right, because it is only true if the structure is completely lossless, and if there are losses, with 1% in this case from the radiation resistance, then it looks like that. So the very simplified model is true only if the distance between antenna elements is an integer multiple of lambda over 2. In every other instance, it is not. This may again show you the reason what is happening here. Imagine you have such a plane wave with a vertically polarized electric field So the electric field has only a Z component, and it's coming towards us here, of course in slow motion here. If we place these two antenna elements, again, half wavelength dipoles with a distance of 1/10 of the wavelengths between them, if we place them in the center of that square, and if they're open circuited, then nothing changes, because these antennas are so-called minimum scattering antennas. And if at the terminals there is no current, then there is no current on the whole structure, and then it's simply as if they are not there. But now, in order to measure something, we have to terminate them. We have to take out energy from the field, and if we do that, the total electric field looks completely different. It's not a plane wave anymore. And the difference between the total field and the incident field, that is the scattered field, is almost as large as the incident field. And that is what in signal processing normally is completely neglected. All the signal processing literature assumes we sense the field with our sensor elements, with our antennas, and we don't change the field in that. When you make a measurement in any circuit, measuring the voltage from a node towards ground, and as soon as you connect the voltmeter, of course the voltage will change. The change may be little. Here it's different, because we would like with our receive antennas to take much energy out of the field. In contrast to the voltmeter, where we would like to take only a very low current out. Okay. Therefore, we have to have a closer look at our physical models. And it has also to do with the way how we compute the energy. When you look in a signal processing in a communications book, you will find there that the signal energy or signal power is defined basically always that you take the squared magnitude of some complex numbers. And these complex numbers normally don't have any unit. There is no volt or ampere or watt coming with that. It's only a number. Is that a useful definition of energy? Well, let's look in the physical world. And the simplest example I can choose here is a one-port a ohmic resistance. And of course, we know how to compute the power flow into that element. It's simply voltage times current as the instantaneous power. And since we have Ohm's law, we can express it, of course, also as a function of the voltage squared and the current squared. And therefore, it's okay. The signal X, which we normally use in signal processing, if we say this is proportional to the voltage, or we can even say it's proportional to the current, everything is okay. The physical power, the true power, and the signal power, which is defined in many books, are at least proportional to each other. They are not exactly the same, but for almost all optimization procedures, that's fine. If I would like to maximize or to minimize that, the proportionality factor is not really important. Even we could take any linear combination of voltage and current, and it still would be okay. But what happens if our signals are vectors? And again, the simplest possible vector I can choose, a two-dimensional one, then the signal processing literature tells you that the signal power is the squared Euclidean norm of that vector, and if you take an integral over that, you get the energy. Is that a useful thing? Well, now my physical model is a two-port. The power flowing into that two-port is the sum of the powers which flow individually in each of the two ports. And if I compute that, in order to compute it, I need to know something about the two-port. I need to know what is in that box, either described by some of the two-port matrices, or if I know the structure. Give some simple structure, then we have some result. And here we see, no, if I choose and say X, my signal vector X is the proportional thing to the voltage vector, it won't work. Even if I take the current, it again won't work. There would be a tricky thing. I could come up with a matrix which transforms that vector, and then it may be okay. So the moral from that story is what the signal X actually means physically is only of secondary interest if it's a scalar case. But it is of key importance, it's essential if the signals are vectors. And especially when in communication we work with multi-antenna systems, we have transmit vectors and receive vectors, and normally what is called transmit power, by taking the squared Euclidean norm of the transmit vector, is not really transmit power. Only in very special cases it may be okay, but in the general case it's not okay. And for that we have a closer look how we should make our models. On the one hand, we have the signals, X as an input signal, H, for instance, as an impulse response, Y as an output signal, theta as noise, and then we have a system function there where the output is the convolution of input times impulse response plus noise. And on the other hand, we have physical quantities. We have voltages, currents, we have electric fields, magnetic fields, impinging waves, reflected waves, and we have laws of nature. And that is what is important, which does normally not come into the play in signal processing. The great laws of conservation which we have in physics. And we have constraints, of course, from the thing. And there we have done make an assignment between the true physical quantities and the complex numbers which we deal with in signal processing, in information theory, in communications. And look at the implications. These assignment which we choose has, of course, implications, and we have to figure out these implications. That is very important. I will show you that with a very simple example. That figure here basically is figure 1 in most of communication textbooks, the AWGN channel. So we have a channel coefficient, and we have an input signal, an output signal, and we have noise. And for the simplicity, I've chosen to make everything real valued here. We need not to refrain to complex valued signals. We can simply do that. But for that example, it's much simpler. Okay. Signal-to-noise ratio, it's always important to define that because there are so many versions of signal-to-noise ratio around, and not all of them are really useful. The signal-to-noise ratio I have used here is simply, in the numerator, we have the variance of the output signal when we switch off the noise. That is, of course, only a Gedankenexperiment. In reality, we can never switch off the noise, but we can compute it, of course. And in the denominator, we have the variance of the output signal when we switch off the input signal, and only the noise is present. That makes a lot of sense. And for that example, where the noise is normally distributed with zero mean and this variance, we see that the denominator is that variance, sigma theta squared. In the numerator, we have the variance of the input signal, and that has to be multiplied with the squared magnitude, with the square of our channel coefficient. When I ask you now, what happens if I reduce the channel coefficient by a factor of 2? What happens to the signal-to-noise ratio? Well, the standard answer is, well, it will go down by a factor of 4 because we have that square here. Well, this is only true if the variance and the channel coefficient are independent. And that's not clear that they are really independent. There may be very well situations where they are heavily dependent. And therefore, we have to figure out how the noise comes into the system, how it interacts with the system, and we will do that, again, with a simple example. I choose as a communication system an ideal transformer with a certain turns ratio. Forgive me for using that letter Ü to designate that, because in German language it's the Übersetzungsverhältnis. Okay? Now, we connect a source on the one side, we connect the load on the other side, and we let both resistances be noisy. So we replace the noisy resistance with a noiseless one and a parallel noise current source. I could equally well have chosen the series version of a resistance with a noise voltage source. They are completely equivalent. Now, what's the next step? We have to do an assignment. So X should be the partner of the generator voltage. Y should be equal to the load voltage. And then we have to look for the implications. What follows from that? Well, then I have to start with a circuit analysis. And again, a student in electrical engineering in the first year should be able to analyze that simple circuit and come up with that equation to see that the generator voltage times some coefficient, which will be our channel coefficient, is the load voltage plus that noise term. So we have here our channel coefficient, we have the noise variable, the random variable for the noise, and we assume that these two noise sources are uncorrelated. Going through that, we see, first of all, that our channel coefficient in magnitude is limited by 1/2, and that maximum value is reached when the turns ratio is equal to 1, when it's a 1-to-1 transform. But the funny thing is, the noise variance will depend on the channel coefficient. It's not independent of the channel coefficient. And when we then look at SNR, as I have defined it, and start out with the maximum channel coefficient of 1/2, we get some signal-to-noise ratio. Whatever that number A may be depends, of course, how large I make the generator voltage. But anyway, if I reduce now my channel coefficient from 0.5 to 0.25, SNR goes up and not down. And that the standard theory would never predict. Funny is enough that the signal-to-noise ratio becomes maximum when there is no signal. When the turns ratio is 0 or infinity. And that's not an error. That is simply that the noise voltage goes down quadratically with the turns ratio, and the signal value goes down linearly. Therefore, the ratio of the two increases. That again should warn you. For information theory, signal-to-noise ratio is the golden calf. It's the one we should like to optimize. Well, if the optimum of SNR is when I have no signal, then it's not useful. So it's also to look at, I need a certain minimum signal power, which is necessary that the rest of the system can operate, and only then it makes sense that we optimize the signal-to-noise ratio. Yeah. Let's now look at the multi-antenna case. The standard thing is, if we have an antenna array here with n antennas, and there is one receive antenna, and assume that they are all close by, such that the distance between each transmit and each receive antenna and the receive antenna is almost the same, only the phase of these different passes will be different, and I can assign a beamforming vector which compensates for that, such that I get maximum signal at the receive antenna. I can go quickly to that calculation and come up with the fact that the transmit array gain will be equal to the number of antennas. That is, again, a standard thing everybody knows in signal processing. And it doesn't depend on the direction, in which direction I would produce that gain. If the array is a uniform linear array, for any direction, front fire, end fire, it will always be the same antenna gain. Question, is that true? No, it's not true. It's only true in very special cases. Here, now I have to skip a number of slides from that tutorial because that would be too long, too many details. Let me quickly go through the important result which I will show you. This is one thing which is important, and what we see here is the following. Only for two antennas, and the axis may be the currents which I send into these antennas, we can compute the radiated power by taking an integral over a sphere which encircles that antenna arrangement. And to make things easy, I make the radius of the sphere large enough that the sphere is in the far field. Then it's easy to integrate the pointing vector around that sphere and to come up that our antenna, our radiated power can be computed by a quadratic form. This is the vector of the currents, complex conjugated, the vector of the currents, and in between there is a matrix. Therefore, it's not the squared Euclidean norm of the current vector, but it's a quadratic form. And the off-diagonal elements in that so-called coupling matrix for isotropic radiators would be the sinc function. For lambda over 2 dipoles, it's something different. The formula is too complicated. I haven't shown it here, but we can compute it analytically, of course. And you see then these off-diagonal elements as a function of the spacing between the antenna elements, that for the dipoles, the green one is not the same, but close to the one from the isotropic radiators. This is important because many people use isotropes in their modeling, and anybody who knows about Maxwell theory knows there are no isotropic radiators. They don't exist. They are only hypothetical elements, but we can have things which are close, and for some analysis it's useful to work with them because it's much simpler than to go with the dipole elements, for instance. So this is one thing, and then the next thing is how should we optimize the beamforming vector for such a system when we, I was a bit too quick now, the optimum beamforming vector now is something which depends on that coupling matrix, actually on its inverse, and of course on the direction for which we would like to produce the maximum signal strength, the maximum receive power. Okay, and for that we look at our final formula for transmit array gain, which actually depends in that vector A. This is the so-called steering vector for the direction, and the inverse of that coupling matrix. Again, at the coupling matrix, when you look there, and when we talk about isotropic radiators, if I plug in that D is lambda over 2, then these two elements become 0, which means the real part of the mutual coupling has a 0, and then it's almost as if the two antennas are not coupled. And then it's the Euclidean norm, because then the matrix, which is in these quadratic forms, is then an identity. But that is a very specific case only. This is not the general answer. And then it's interesting to look what kind of array gain do we get for a uniform linear array in end fire, and what do we get in front fire. And again, in contrast to the general belief, the array gain depends on the direction for which you would like to produce it. It's not independent. And now again, I would have a question for you. For which of the two situations you would expect a higher gain? When the uniform array is before me and I'm looking in this direction, or I arrange the uniform array this way and I'm again looking in this direction? This is for end fire, and what we see there is, again, at distances which are integer multiples of lambda over 2, the gain is equal to the number of antenna elements, which is the factor which parameterizes the curves here. But if you make the distance smaller and smaller again, it goes up to n squared. In front fire, it's not that good. Note that this is a different scale here. So in front fire, even with 6 antennas, we can't do what we can do in end fire with 5. And it looks a little bit crazy, and is such that the best distance becomes closer to a full wavelength the higher the number of antenna elements is. That end fire is better, you should have known. Think about in the past when we had still standard terrestrial TV reception with these Yagi-Uda antennas, which are multi-element antennas, and they always were in end fire direction, pointing to the transmitter, and never in front fire. Okay, I guess, yeah. One important thing is antenna experts. I'm not an antenna expert. I'm a guy who tries to bring together signal processing information theory with electromagnetic theory, and using as a mediator between these areas circuit theory, because that brings the link between these fields. Antenna experts told me, yeah, we know that this is normally called super gain or super directivity, but it doesn't work. It doesn't work because the losses will kill you. Therefore, we are looking at heat loss in antennas and are looking what happens there. That is the last example I'm showing you. This is for 4 antennas and beamforming in end fire direction, and therefore we see with lambda over 2 we have a gain of 4. With very small distances we have almost 16, and that is for the lossless case. And if I now introduce heat losses, and that amount of losses we have computed accordingly, assuming that it's a copper wire and we're at 3 gigahertz and take the skin effect into account and all that, then we get the green curve. And it's true what antenna experts tell you, losses will kill you. It's true if you overdo it, if you make the distance too small. One has to do 2 things to exploit that. We have on the one hand optimized the distance. What is the optimum distance I should choose? And in these distances I have to take into account that the design of the beamforming vector has to be optimized for that specific situation, including the losses. So it's not the same formula anymore, which I've shown just before. And what we see there, if I'm going for approximately lambda over 4 instead of lambda over 2, I can get almost all the gain which is there. And that is something which we should use in mobile communications, which would extend range. There are a number of other things which I, because of lack of time, can't tell you. We can, with small arrays, have good diversity performance. We can do multi-streaming, and we will have nice capacity regions. So these are all the different possible performance figures which people use for antenna arrays. Here I have chosen that with the array gain because that I think is the most simple one to see. So let me summarize. Antenna coupling, I think, is essential for array gain, and we have to take into account antenna coupling as a complex transimpedance between antenna elements is never 0. Because if it would be 0, we would have no communication. Think about a SISO link with one transmit and one receive antenna. I put some current into the transmit antenna, and I measure the voltage at the receive antenna. That is the transimpedance, the mutual impedance between the two antennas. If that is 0, then I have no communication. So coupling is there even if the antennas are hundreds of meters apart from each other. Of course, it becomes more prominent the closer they are, and when we, especially in the 5th generation, would like to go to very many antennas, and therefore make the array compact, put antennas closer and closer to each other, that is an effect which we cannot neglect. Okay? So the array gain can grow superlinearly with antenna number. Coherent beamforming doesn't work. We have to really optimize. That's not a very complicated problem. It's simply a generalized eigenvalue problem which we have to solve in order to find the optimum beamforming vector. Heat losses are important. That's no question about that. And we have to take that into account. But there are gains to be achieved. And what are the important ingredients again? The main thing is we have to consider ports as the interfaces between different parts of the system, not a single terminal with one variable there. At a port, we always have two conjugated variables, voltage and current, E field and H field, electric and magnetic field. And the two determine the pointing vector, which tells us about the power flow, or incident and reflected wave. Only the two together tell me how much power flows across that port. With one single element there, which is x, and I say, let's take magnitude squared of x, that is in many cases not important. So each port is described by two variables. The relationship of the port variables are deduced from the laws of nature and from the physical and technological constraints. And the signals are assigned to these physical port variables. We have to make clear what is x and what is y in our equation. Y is channel matrix times x plus noise. Then in one of my lectures, I asked the students, where in the system would you put a measuring equipment to measure the transmit vector? Where is that vector x in the transmitter? What would you need? A voltmeter, an ampere meter, a power meter? What is it? X is normally the input of the D to A converter in the transmitter. And Y normally is the output of the A to D converter. And the question what X has to do with the transmit power is a complicated question, which we have to address and have to solve. Otherwise, we will not have the proper transmit power. And I'm not sure how many people really, with the smartphones and the base stations, have really measured transmit power. I'm hesitating that has actually been done. Because to do that is complicated. You have to go with a sensor antenna on a sphere around the base station, and in this way collect all the power contributions and average them out over the area of the sphere, and that is transmit power. Normally what people do is they disconnect the antenna and connect a power meter to the output of the power amplifier. Well, in that sense, of course, mutual coupling is gone because the antenna isn't connected anymore. So these are the things where I would like to put a bug in your ear. to say it's important that we look at the physical foundation of our science which we work in. It's not only about complex numbers in communications and in information theory. We have to make a link between these complex numbers. And all that what is done in these many publications, it's useful. But we have to make the link to physical reality. That is the key message, and I thank you for your attention.
Okay. Now we can go to the part of the questions. So anyone would like to make any questions, please? No, okay, any questions? Maybe. Yeah, one thing that you mentioned, I'm going to pass you the microphone later on. One thing that you mentioned, Josef, is that people that work on antenna development, they say that the super array gain is not possible, so on, right? And the question is, have you tried or have you worked with some people that really implemented, because I think most of the results here are simulation results, if I'm not mistaken. If you really measure that, maybe I can pass the microphone to you, 1 second.
No, it's not simulation. It's analytic analysis. So it's really only theory-based. True, with the losses, that is simulation. In the last year, we have run a joint project with the chair of high-frequency engineering in Munich and with a large telecom infrastructure company and have produced such compact arrays and have designed decoupling and matching networks. That's a topic which I haven't touched upon because it, again, is beyond the scope of this short presentation. And the results which we have for arrays with 3 and 4 antennas is well within what we can expect theory and measurement with measurement accuracies at 3.6 gigahertz. So I'm quite sure with these small number of antennas we can do it. For large numbers as we expect them for 5G with massive MIMO, I'm not sure about that. That would be the next step to think about. But anyway, even if we not exploit that, we have to take into account that there is mutual coupling and include it in our analysis. It will tell us what we get. Even if we are not making it that small, it's there. And therefore, there is never an excuse for neglecting an effect where you don't know how important that effect can be. Okay, thank you.
Thank you very much again. Okay. Now we're going to the next presenter here.